Hi, I'm Ed Spears with Eaton, and today we want to talk about the technical details of how eco mode works in modern UPSs. So on the board here we have a one-line diagram of a traditional double conversion UPS, the rectifier, the inverter, the static switch, and the critical bus output. So in traditional eco mode, the plan was to basically turn on the static switch and shut off the UPS. The problem was it takes too long to start a UPS from shutdown mode. How do we do that traditionally? Well, you got to close the input contactor. You have to wait for the rectifier to ramp from 0 to 700 volts DC. It's got to do that slowly over about 30 seconds or else you'll stress the capacitors connected in the DC link between the rectifier and the inverter. Then, once the 700 volts appears, the inverter can start, take DC and make AC, but this AC output of the inverter has to be in sync with the critical bus before we can close the output contactor. That's another delay of 10 to 15 seconds to wait for sync. So, close the input contactor, ramp the rectifier for 30 seconds, turn on the inverter, synchronize the inverter, finally close the output contactor, and you have an output from the UPS. The process takes 2 to 3 minutes. It's much too long. So how does it work in a modern eco mode? Well, the static switch will be closed if the incoming power is close to perfect, allowing power to flow directly through from input to output, and our output contactor and input contactor remain closed. That gives us two benefits. I don't have to wait for the contactor to close, and I don't have to hope it'll close. A contactor that is closed can't fail to close. It eliminates the mechanical component here. So with closed contactors, I have voltage here, and I have voltage here. The rectifier and inverter are suspended, but the inverter is still generating its gate commands for its main power transistors. It's not actually firing those transistors, so it's not using any power. But the gate command signals are already in sync with the output here, so I don't have to wait for sync when I flash the inverter on. But what about this rectifier that has to charge these capacitors over 30 seconds from 0 to 700 volts? How do we do that? Well, if we look at the schematic of the inverter's job is to take DC and create AC. Schematically, it looks like this. Here's positive and negative DC, and the inverter transistors create phase A, B, and C, a three-phase AC output. But if I'm not gating those transistors when I'm suspended, the transistors disappear from the circuit. They're open switches, leaving me with 6 diodes in a bridge rectifier schematic. This means that the inverter diodes will take the existing AC at this point, rectify it, and create the 700 volts DC that we need to keep the caps charged and to quick start the inverter when necessary. So in eco mode, I'll have power through the static switch. If the incoming power becomes disturbed, I can flash on the rectifier and the inverter, and I can do that in as little as 2 milliseconds, including turning off the static switch. Is that fast enough for the critical devices that we're supporting here? Well, the guidelines say any transition should be less than 20 milliseconds. The reality is, the faster the better. The main reason for having eco mode is saving money. So just as an example, let's take a look at a medium-sized UPS. Here we have 250 kilowatt UPS compared against a legacy UPS that's 93% efficient, using an eco mode UPS at 99%, and the savings at 11 cents a kilowatt hour are $24,500 per year of operation. Significant savings, and will actually repay the cost of the UPS within 2 to 3 years. By far the biggest concern with eco mode UPS operation is the observer has trouble accepting that we can in fact transition from static switch operation to double conversion operation in less than 2 milliseconds. So we use an oscilloscope trace as proof. Here we see the input power disrupted coming into the UPS, and the output power here. At the same point, we do not go to 0 volts, but continue to produce a three-phase output. And the transition time from utility power to inverter power is in fact less than 2 milliseconds. One of the primary concerns with eco mode UPS operation is what if I have a disaster like a lightning strike on the input terminals of the UPS? So this graphic shows how that would look. I have a 6,500 volt very narrow spike here on the input of the UPS in eco mode, but the green line here shows only a small voltage aberration at the output of the UPS. An eco mode UPS, a good one, can actually suppress lightning strike style surges. So what the graphic shows is, even when we impress a 6,500 volt spike right on the input terminals of the UPS, and even though the static switch is closed in eco mode, we're able to attenuate that surge at the final output, shown by the green sine wave, to only a few volts. So in fact, the UPS is able to suppress lightning strike style surges, even in eco mode. So if you're considering using eco mode on your UPS, there's 3 criteria that should be important. The first one is transition time. The time it takes from static switch operation to traditional double conversion should be less than 4 milliseconds, ideally less than 2 milliseconds, or 2/1000ths of a second. The next one is efficiency. The system efficiency in eco mode should be greater than 99%. And the last one is, can your eco mode effectively suppress lightning strike style surges and protect your critical devices even without surge protection on your building entrance?